Welcome back. I'm going to be completing part B of homework 2 for process dynamics and controls today. And today we are going to be simulating another tubular system, this time a reactor. We're going to discretize it into 200 CSTRs, this time versus the 100 that we were previously working with. And we are going to use the Google JAX AI framework to implement a lot of this code to try to speed up the calculation a little bit. And to get started here, I've went ahead and got all of our tools that we're going to need from the GitHub, and I have set the print options for our JAX NumPy. And what I'm going to do now is I'm going to go ahead and paste in all of our constants we're going to need. So going through these are n equals 200, that's our 200 CSTRs that we're going to use to simulate our tubular reactor. Our Q is, of course, our initial volumetric flow rate in. Our CAN is our initial concentration coming in. Our TN is our initial temperature coming in. The total volume is the total volume of the entire reactor, which we're going to divide by N to get the volume of each of our independent CSTRs. And then, of course, we've got our rho, our density for we've got coming in. We've got our constant C. We got our enthalpy of reaction. We've got our E times our K naught for our Arrhenius equation eventually, and then our internal energy we're going to use for a lot of our heat calculations later on. And all of this will sound pretty familiar if you go back and look at Process Dynamics and Controls Homework 1 Part C, in which we simulated a continuously stirred reactor with these conditions. We're just now going to apply that to a tubular reaction discretized by 200 CSTRs. So let's go ahead and get started. All right, so getting started here, we're going to go ahead and define our right-hand side as a function of t and r vector. And as usual, we got to define our vectors. So we're going to say c and t r and mp dot split our vector into 2. And then we've got to create our change in concentration and temperature values. So we're going to say our DC for now is just going to be np dot zeros size n. And our dt is also going to be np dot zeros size n. Moving on from this, we can do all of our mass balance stuff. So if you remember from before, we figured out that our DC initially, so our DC at 0 is going to be equal to our Q times our C in minus our C at 0. All divided by V minus our K at 0 times our C at 0. Moving on from here, we can find our change in C for the rest of the CSTR. So we can say our DC, all of the values following 1 are going to equal our Q times, this time around, our C -1 -1 minus our C at the rest of the values, all divided by V, and again we're going to do minus K, the rest of our K's times all of the rest of our C's. All right, now that we have our mass balance, we can go ahead and move on to our energy balance. So we can say that our dt at 0 is going to equal our Q times our Tn minus our T at 0 all over V. And then we're going to subtract our change in internal energy. So we're going to say our UA times our T0 in our first CSTR minus our TC all over rho times C times V. And then finally, we're going to add our neg HR, negative change in enthalpy, times our C naught, K naught I should say, first, times our C naught, all over V times C. Fantastic. Wait, this is rho times V. Perfect. And then we do the exact same thing for the rest of our temperatures. So dt T1 and so on is going to equal Q times, I think it might have gotten it perfectly there. Yeah, T at -1 minus T, the following values, over V, all minus UA times T1 and so on, minus our TC, all divided by rho times C times V times V, all plus, yet again, our negative enthalpy times K at the rest of our values. Oh man. Times C at the following values divided by rho V. So the exact same equation as above, just for the rest of our values, not just our initial state. And that is our energy balance. Just realized I made a little bit of a mistake here. Need to change these to C, not V. It's getting my equation a little bit confused. And then I'll go ahead and stick that into parentheses. Fantastic. And then finally, we're going to go ahead and return our numpy.r, our dc, and our dt to put those into an array. We should be all good to shift enter, move on to the next part. Moving on, we are going to implement the Google JAX AI framework using our JAX.jit, our just-in-time, and our JAX.Jacobian to speed up our numerical simulation a little bit. And to do that, what I'm going to do initially is I'm just going to grab all of this previous code that we've written up here, put it down here, because the syntax is very similar. You only really need to tweak a couple things up here to get to our Jacobian and our just-in-time. And the things that we need to change, all we have to do is put J's in front of our NPs for our JAX NumPy. And then here where we have our DC at 0, instead we're going to say DC equals DC dot at 0 dot set, and we're going to put this entire function within there. And then I'm going to do the same thing with each of the rest of these. So yet again, I'm going to get rid of R1 there and change it to DC dot at this time 1 comma dot set around there. And then I'm going to do the exact same thing with our t's. So delete this. We're going to say dc dot or dt dot at 0 dot set this entire function here. And finally, we're going to do it with our last dt for the rest of the values of n. So we're going to say dt dot at 1 comma dot set. Yet again, put this big function inside of there. And then I'm going to return jnp.r or dc or dt. And then finally, we got to do our just in time, our JIT. So to do that, well, first I need to define this as a different function, RHS JAX. So we're going to define RHS JAX is going to equal JAX dot JIT RHS JAX, and then we're going to say that RHS JAX Jacobian is going to equal jax.jit RHS jax.jacobian RHS jax. Shift enter. And it looks like that all worked. So now let's move on to getting ready to plot this out. I just realized I made a little bit of a mistake. Forgot to apply our Arrhenius equation in here, so I need to have RK equals RK not times MP dot EXP of R negative ER over T. I need to put that in for both our normal right-hand side and our jax numpy. Except, as I said earlier, change that MP to JMP. Realized I did not have the 1 here, which would in fact make some issues when it came to doing our solve IVP, as the solve IVP is going to be expecting only 1 value there, where instead it was going to get 2. So I went ahead and fixed that. But moving on, we can now go ahead and create our time plot and go ahead and put in our solve IVP function. So to get started there, I'm going to say our n times is going to equal 100. It's just the amount of iterations that we're going to see on our plot at the end. Let's say our dt, or change in time, is going to equal our t end divided by our n times. And then, as usual, we're going to create our t plots using np dot line space, going from 0 to our t end with n times iterations in between. And moving on from there, we can go ahead and have our result defined as scipy dot integrate dot solve IVP with our right hand side JAX version, our TN are going from 0 to TN with initial values np dot r underscore. Going to go from C naught and T naught. And then we're going to set our method equal to our Gadao. and our dense output equal to true. And finally, we're going to put in our Jacobian. So we're going to say our jack is going to equal RHS underscore jacks underscore jack. Now that we've got all of that in there, we can go ahead and create our overall plots. So we'll say like figures, or I can't even think of a name. We'll just say plots is going to equal res.solve for our t plots. And then later on, we can crack this plots into our C plot and our temperature plots. Now we're all good to go ahead and start our plotting. So to do that, I'm going to split up that plots plot I just made right there into our C plot and our T plot for temperature and concentration. So to do that, I'm going to have, try to remember which comes first. It's our concentration. So I'm going to have our C plot, T plot equal MP dot split plots into 2 axis equals 0. All right, now we're ready to make our figure. And to do this figure, we're going to do another for loop just because it makes it easiest to plot each individual thing for each end time that we have up here. So to start, we're going to do figure equals make subplots. And then we're going to do for t index in range n times. We are going to say figure.add scatter. And we're going to have our x equal mp.arange n. Our y equals c plots, or c plot at t index. We're going to have rows equals 1, calls equals 1. Now we're going to do another fig.add scatter. To x again is going to equal mp.arange. And this time our y is going to be our t plot. Cool. We're going to put this in the second column. Alrighty. Let's show our figure. All right. What is happening here? Sorry about that. Ran into a couple little issues there. I had an S at the end of these rows and columns. I forgot to put 2 different columns in our subplots, but now we've got everything good and figured out, all put together, and we've got some beautiful graphs here. So try to explain this. As you can see on our concentration plot, the concentration flies way down right as the temperature goes way up, which makes sense. It's an exothermic reaction. It gets super hot as it reacts out, which could be a little bit dangerous in a plant setting, which is why it's important to have some good controls on there. But as you can see, as the temperature starts to fall again over time, the concentration steadily starts to equilibrate a little bit. But if you can see, these graphs make perfect sense because we have this jump in temperature caused by a rapid drop in concentration. And I believe that is the end of homework 2, part B for process dynamics and controls.